inheritance patterns tonight. How many of you think that you know anything at all about X inheritance? Okay, now come on, now somebody knows something, right? Okay. How many of you know that your autosomal test results include X results? Okay, but if you're female, they include both of your X's, and if you're male, it includes one of your X. And on GEDMATCH, there is sorting according to autosomal 1 through 22, and there's also that chromosome 23, or X, sorting as well. So we're going to talk about that tonight. There's a different inheritance pattern for the X chromosome than there is for autosomal DNA, or for mitochondrial, or for Y DNA. So we're going to talk about that also, so that we have a little bit of clarity there. So what is DNA? We've had a lot of discussions. I'm sure that you've had tons of discussions about what is DNA, but I think it's important to clarify that we're talking only about nuclear DNA. We're talking about autosomal DNA plus the X. We're not talking about mitochondrial DNA. Mitochondrial DNA, even though it's called the maternal line, and we get our X from our mother or our father, but sometimes we think females have more X DNA, and we think that's maternal. They're two different things. Mitochondrial DNA comes from a different place in the cell. It's actually a ring. It's not a stepladder like you're used to seeing. It's a ring. It's almost like a circle. And mitochondrial DNA has a different inheritance pattern. So we're talking about nuclear DNA, and we're talking about autosomal DNA. For your genome, you have 22 autosomes, but you also have those sex or gender chromosomes. If you're male, you have an X and a Y, so you do have an X. It has a particular inheritance pattern. And if you're female, you have two X's, and that also has a particular inheritance pattern. So we're going to talk about both of those. There's two cases that we're going to talk about, if you're male and if you're female. There are rare cases where someone inherits more than two X's, or there are some men who have two X's and a Y. It's not something you'd be able to differentiate from GEDMATCH. It's fairly rare because normally in those situations, it wouldn't be a successful pregnancy, but we all know that there can be chromosomal abnormalities and still have a birth. So I don't want to leave you with the impression that there are only two cases. There are some others, but that's typical of what we see in our work in genetics. Mitochondrial DNA is passed from mother to children, so men don't pass it on, but we want to talk about all four kinds of inheritance because whichever test you take, whichever tools you use, whichever matches you have to understand the four different inheritance patterns. So mitochondrial DNA is from mother to children. Men don't pass it on, although men do have mitochondria. The mitochondria in the cell is the energy producer of the cell, and your cells as men do work, just like our cells as women do work. So you do still have mitochondrial DNA, you just don't pass it to your children. The reason why the egg is so much larger than the sperm is because the mitochondrial DNA is in the egg. That's how you get it, is in the egg from your mom. Autosomal DNA, chromosomes number 1 through 22 are in pairs. So you get one of each pair from each parent. So that's a different inheritance pattern. You get one number 1 from mom. You get one number 1 from dad. You get one number 22 from mom. You get one number 22 from dad. So that's a different inheritance pattern than mitochondrial DNA. The sex or gender chromosomes for Y DNA, how many of you have done a Y DNA test? A few, or you've managed some for the men in your lives? Okay, so the Y DNA is passed from father to son intact, and women do not have Y DNA. So that's yet another inheritance pattern. It's different than mitochondrial, even though mitochondrial DNA and Y DNA are both very stable for very long periods of time, and they have a similar inheritance. Y DNA is only in men. It's from father to son to son to son through that line. Mitochondrial DNA, don't forget, it goes from mother to all of her children, and then from the next mother to all of her children. So it does inherit, it does get passed on to the men as well as the women. And the last one that we're going to talk about tonight is xDNA. xDNA is passed from father to daughter intact. So whatever xDNA you get from your dad is in sperm and it's intact. He only has one X to contribute. If he contributed a Y to you, then you would be a boy. You wouldn't be a girl. So if you're a girl and you have an xDNA from your dad, you got it intact from your dad. xDNA from your mom has a different kind of inheritance. You can either inherit one of her X's intact, the second one intact, or a mixture of the two. So it is unlikely that it's more likely, let's say, that you would get a mixture of the two. But it is possible to get one from your mom and then get the other one, maybe and your sister has the other one. So maybe you don't xDNA match your sister, but you're still sisters. You just inherited it differently. So we're going to talk about that inheritance pattern. We're also actually going to watch a little video on Khan Academy about how that happens. I think most people are visual, and it helps to kind of see that instead of me just talking about it. So we're going to do just a little short video on that. But let's talk for a minute about the DNA strand made of base pairs. Most of you who've been around this group long enough probably already know that your autosomal test is testing roughly 700,000 markers of your 3.4 billion spots in your DNA, but it tests the 700,000 places where we're different, and about 99% of our DNA is the same. We're actually about 50% of our DNA is the same as a banana. So we have a lot of DNA overlap. We don't need to test the places that we're the same. We don't need to test the places that give us all 2 ears or 2 eyes or 1 nose. We just need to test the places that are different. So that's what DNA testing is. How many of you have opened up and looked at your raw DNA file? I know when they tell you to upload to GEDMATCH, they say don't open that zip file. But as soon as you upload to GEDMATCH, you can open that zip file. There's no prohibition against that. But if you open up your zip file, what you're going to see in your raw DNA file is you're going to see, I've got some things here to show you. There's a marker that's being tested, and they're in order of the chromosome. The chromosome number is listed. The position is the base pair position that's been identified that they're testing. Remember, they're not testing all of the 3.4 billion places where we have base pairs. Only 700,000 is what they're testing. And then allele 1 and allele 2 are the base pairs received in the forward position. Now, if you don't know too much about DNA, when it's read, it's either read forwards or backwards. And so if you look up here in the, I think I have something on here. Yeah. In the first line up there, in the first position on chromosome 1, if you get a TA from one parent and a TA from the other, the test reading forward says you get a T and a T. If you read it backwards, you get an A and an A. So everyone is in agreement that the testing companies are all going to read in the same direction, and that way we're all reading forward, or down the spreadsheet, so to speak, or down the DNA strand. And so that way we can look at those alleles that you get, one from mom, one from dad. Now, how many of you have tried GEDMATCH's phasing? Has anyone tried that? Okay, just a few people. Phasing, what phasing does, and I think it's a real good place to show it here visually, phasing will compare your test with either one of your parents or both of your parents or children. So it does a generational connection between your DNA and theirs. So for example, I have both of my parents' DNA tested, so I can phase against my dad. And then what happens in GEDMATCH is it makes me a whole separate kit of just the one allele each time that I got from my dad. So the one that matches his is its own kit, and then the one that matches my mom is its own kit. So that can be a really useful tool on GEDMATCH when you're trying to sort between which side of the family or come to some conclusion about why you have a match. Does anybody have any questions so far? Yeah, go ahead. Can you phase with the siblings? There is a sibling kind of phasing. It's a little bit different. The sibling phasing is really part of something a little more complicated called the Lazarus Project. So you can sort of resurrect that parental profile by uploading siblings, first cousins, things like that. But it's one of the tier 1 tools. It's not complicated, but you do need as many people as you can get in order to do that, because otherwise there'll be blanks. There'll be unknowns. Yes? One of your cousins was adopted, okay. Okay. If she is doing, so your question is if she, I'm just repeating it for the recording. If she has her kit and she's adopted, but she has a biological child, then what she'll get actually is for her child a phased kit of what's her contribution to that child and what's the dad's contribution to that child. That's not going to give her parental information. Well, the matching is different than phasing. Phasing takes my DNA sample and splits it in two, basically, and says, this is the part your mom gave you, so this is the egg part. This is the part that dad gave you, the sperm part. And it's pretty close to about a 95% accuracy in terms of, right, so you can do that with your own biological children, but what that does for them is it splits their DNA according to their mother, you, and their father. Whether you have their father or not, you're still going to be able to sort just using yours. You can do DNA phasing with matches. Well, the questionable matches from an adoption, I wouldn't start with phasing. Let's put it that way. Phasing is a multi-generational tool. So you want to do that with her and possibly aunts and uncles. You could do that if you've located biological aunts or uncles. Yeah, it's just not it. And mom is not available to be tested. Oh, okay. All right, so you haven't approached bio mom. Okay, so you have a lot of other things to do before you do phasing. Phasing is a little further down the road. Well, the xDNA kit could help you. So we'll do a little bit of case study here on the xDNA because that's part of GEDMATCH. So we'll do some of that tonight. So hang in. Okay. So there's no way to know which allele came from which parent without either segment analysis, which is something else you can do on GEDMATCH, or phasing, which is something you can do on GEDMATCH. So you don't know which of the two you get. Now, if you get a T and a T at that first spot, then it doesn't matter which one gave you which one, right? But if you get the next line, the A and the G, you want to know which parent gave you the A and which parent gave you the G. The only way to determine that is either through phasing or through segment analysis. And both of those, is phasing a tier 1 tool? I think phasing's not, but segment analysis is. Sometimes those lists move a little bit. But it's worth the $10. I mean, for those of us that use it all the time. Plus, even if you don't use the tier 1 tools, it's kind of worth contributing to the greater good, their bandwidth. You know, they're not making money on it. They're run by volunteers. They're not a for-profit company or anything. So it just contributes to their bandwidth, so you don't have to sit there so long and wait for results. Okay, so let's talk about the different kinds of X inheritance patterns. Remember I said earlier that males have a different pattern of inheritance than females. So let's talk first about a daughter. Both men and women have xDNA, but women have two X's. One is completely intact from father. Do you see where it's blue there? Father's xDNA, and it's blue. It's completely the same, an identical chromosome. That's because his xDNA comes in his sperm. So it's the same X that he already has. For the mother, you can see there's two different shades there, pink and red. Hopefully you can see the colors pretty well. But from mom, you can get either the top one, you can get the bottom one, or you can get a mixture of the two. There's no way to really know what the mixture of the two is unless you have a lot of sisters, you need to sort it out. Kathy posted on Google Drive, and I think or maybe it was the announcement about the meeting. She posted, I think it was Blaine Bettinger's charts. This is from Steve Morse. This one has the X chromosome pattern for men. And we'll spend a little bit of time talking about this later, but I just want to show you that the X pattern of inheritance doesn't involve all of your ancestors. It only involves the ones who submit different X chromosomes at different generations. So there's a point where your dad gives you an X DNA if you're female, and there's a point where your mom gives you an X DNA if you're male. But understanding the inheritance patterns between male and female can greatly reduce the number of things you're investigating. If you look at this chart, everything that's pink and blue, you're going to want to analyze, but all the things that are white in terms of your fan chart are people who didn't possibly contribute to X-DNA inheritance. So those are, the negative result, remember, is just as important as the positive result. Ruling things out is always just as valid as finding something new and exciting. There's a different chart for women, and we'll talk about that in a minute. But if you want to talk about how you inherit your X-DNA from your mother, think about it this way. Father, having a son, is not contributing any X-DNA at all. So the son is just getting either one, the other, or a combination from mom. If you look at the daughter, she gets the father's X-DNA intact, and either one, the other, or a mixture of X from her mother. So those are two separate things. Those are two different inheritance patterns. It's not likely that it's a 50-50 split. We want to think about that because we like things nice and neat, but science is messy. You just kind of have to understand science is messy. Here's another chart that will show you a little bit more about the generational impact. So when we're talking about a combination of mom's DNA passed on to her daughter, we're talking about a term in science that's called recombination. It happens with chromosomes, but in the X inheritance pattern, it only happens to women in chromosomes and what's passed down to their sons or daughters. Dad's DNA does not recombine. There's nothing for it to recombine with for the X. So if we look at here at grandfather, do you see grandfather on the left, the green? You don't see any green anywhere, right? He's not a contributor to his son's DNA. Not at all. So that's where part of that white, that whole part of white on your chart gets kind of washed out because there's nobody there contributing. Grandmother can give a mixture of her two X chromosomes to her son, and then that can be passed on intact to daughter. So if you see father's mixture from grandma and daughter's contribution from dad, exactly the same. And over on the mom's side, the mother gets an exact copy from her father, a mixture most likely from her mother, and then her daughter gets a mixture of the two she has, so even more of a mixture. So you can see how there's mixture after mixture after mixture in women, but that's not happening to the same extent in men. So those are significant things that you need to understand and know how to interpret. We'll look at some charts on GEDMATCH and kind of hopefully make that point a little clearer. Sometimes there's one chromosome inherited intact from mom. It's not typical, but it does happen. It's called non-recombination. So if you look at this one here, grandfather donated to mom one chromosome of X intact, and grandmother had a combination to mother. But if you look at what mother contributed to daughter, do you notice here that daughter got one chromosome completely intact that matches her mom and nothing of the other one. So sometimes we're puzzled by why people don't match. I know they're related, but, I know she's my sister, but, I know he's my brother, but, that's what explains a lot of those but situations is the non-recombination or the different recombination. There also could be a case where mom gives part of her X DNA to one son in a split that's a completely different split from the other son, so these two sons don't match anywhere on the X DNA. So you're looking at the X DNA result on GEDMATCH and you're saying, wait a minute, they're a zero match. Or maybe they're a 2 or 3 centimorgan match, just a very small overlap. That's just because when mom's X's recombined the first time to make the first egg for the first son, it was a different recombination than what happened to make the X for the second son. So they're just different cases. It does happen. So just because an X match or doesn't match, it's significant, but it's not exclusionary. It doesn't mean that your brother's not your brother. So don't leave with that misimpression. This is the X inheritance span chart for females. And again, Kathy posted these online. It's a little bit more, quite a few more people to investigate, but it's still not the entire chart. So it can really narrow down. When someone says, what family names, and you're doing X comparison, you don't have to give all the family names. You can just give the ones that are in certain spots here that could have been the person contributing the X DNA. So that'll help your search. All right, let's do the video. It's a short video on recombination. It's not particular to X DNA, but I think visually you'll be able to see what we're talking about when the X's recombine and can recombine in an infinite number of ways, pretty much infinite. So I'm going to make this bigger. There we go.
We have these 46 chromosomes, and beforehand each chromosome probably looks something like that. That's the centromere middle. And then, as meiosis is beginning, they will duplicate into, each chromosome will duplicate into something like that. That's again that centromere middle. So we have these 23 purple chromosomes. We're going to see that these are the maternal chromosomes. They come in homologous pairs. And the nucleus that we're looking at must belong to the cell of the male, because right over here you can see that is the Y chromosome. It's a bit smaller than most of the other chromosomes. I'm going to digress just for a moment to clarify a very common point of confusion, and that is that if you look over here at these two chromosomes, well, this is considered one chromosome, but so is this, called one chromosome. And this can be confusing because this is only one chromatid, and this is two chromatids, so why are we calling them each one chromosome? And the answer to that question is because we count chromosomes by the number of centromeres. So this single chromatid has one centromere, but these two chromatids are attached in the middle by one centromere, so we also call that one chromosome. Just keep that in mind. It's just a technical point to know that even though they're different, they're still both considered one chromosome. And in this chromosome, the two chromatids are duplicates of each other, so it's just a copy of itself. Anyway, back to our nucleus. So we have these 46 chromosomes, 23 homologous pairs, and the chromosomes are not necessarily arranged in the way that I drew them. I just drew it that way for the sake of organization. But we have these pairs, and we're going to focus on one pair of homologous chromosomes. But I want you to keep in mind throughout this video that whatever we're describing that's happening to this pair of homologous chromosomes is also happening to the other 22 pairs of homologous chromosomes. Just that it would be too hard to depict in a video how that's happening, but keep in mind it's not just happening to the pair that we're talking about, but what we're just going to be describing is happening to all of the pairs of chromosomes in the nucleus. So here we have our pair of homologous chromosomes, and during prophase 1 of meiosis, the homologous chromosomes pair up with each other and form a unit called a tetrad.
It's a lot of sciencey jargon, but watch the visual.
Means 4. And the student has 4 chromatids, right? 1, 2, 3, and 4. And the process during which the homologous chromosomes pair up with each other is called synapsis. So during synapsis, the homologous chromosomes will get a little bit closer to each other, something like that. And at a certain spot, they might actually cross over or overlap. I'm going to circle that spot, and that's called the chiasma. And in some cases, another thing happens, this protein complex that resembles something like a railroad track forms. We'll see in a minute why. And this is called the synaptonemal complex.
Again, more vocabulary. But the visual is important. You see where it overlaps?
You can actually see the word synapse in there because this happens during synapsis. So we form this synaptonemal complex, and with the help of the synaptonemal complex, these 2 chromatids, the ones that are crossing over, will actually swap material downward of that point. So we're going to get something that looks like that. Look at how the purple chromosome now has some blue over there, and look at how the blue chromosome now has some purple over there. And the way that happened was that the DNA in the chromosome, actually some bonds in that DNA broke, and the DNA is just kind of swapped places. So what we just described, this process by which the 2 chromosomes swap information, is called crossing over.
We're going to stop it right there. There are maybe a couple more minutes, but I wanted you to see visually. This point of crossing over recombination happens all the time in every pair of chromosomes, in chromosomes 1, the set of chromosomes 2, and it does happen with the X chromosomes as well. And so that's how you get a chromosome from mom that's a combination of 2 of her X's. Does that kind of clarify a little bit? It is possible that a child could get just the pink one. It is possible the child could get just the blue one, whether male or female. And it is possible that could get a mixture of the 2. And it doesn't necessarily have to be a mixture of the 2 where they just overlapped once. They could overlap actually more than once. So there could be more pink, purple, or blue, purple. I guess she said purple. Blue, purple, blue, purple. So it's not typical. It's typical that it's like this, that there's just a piece that they swap. So that's what recombination is. I know that was a lot of jargon and everything, a lot of sciencey words. Don't let that intimidate you. That's what we're talking about, is that crossing over and how maybe you and your sister could have gotten different. So let's recap what we've talked about so far before we get into some of the GEDMATCH kind of things and how do we use it and when do we use it and that sort of thing. So men have 1 X chromosome inherited 100% from mom. Men have 1 Y chromosome inherited from dad. Women have an X inherited 100% intact from dad. And women have an X chromosome that's inherited from mom that can be one of those 3 cases. 100% of 1 X, 100% of another X, or more likely a mixture of the 2, but not a 50-50 mix. Very rarely a 50-50 mix. It's usually something that happens around the ends of them. So this is the point where I say, okay, we've talked about a lot of science words and things, but you can do this. Kathy and I both have spent a lot of time in GEDMATCH. A lot of you probably spent a lot of time in GEDMATCH. There's always something new to learn. But if you can get past your habit of opening your screen, looking at your matches, and saying, I don't know what to do with this, and then closing it, then you've won half the battle. I do a lot of speaking engagements where people come up afterwards, they open up their laptop, they scroll up and down, they show me their matches, and they say, I don't know what to do with this. And I said, right, keep coming back, because eventually you'll know what to do with it. And I can't do it for you. It's something that it requires recognizing patterns and organization, but you can do it. Okay, so don't let the science stuff intimidate you. There are 3 steps to being successful. Organize. Nobody really, well, unless you're OCD, you probably don't like to talk about organization, but if you're organized and you can analyze and look for patterns, you got this. It's really not a difficult thing. Now, one of the things I put together for tonight, Kathy had sent out in the email and uploaded to your Google group, is kind of a case study. It was several different pages, I think it was maybe 14 pages or something, where I went through my GEDMATCH matches, looking at the people I knew versus the people I didn't, and tried to determine which side of the family they came from. Now that's something that's difficult to do in a presentation on screen. If we have time, we might go through some of that tonight, just to kind of give you a jump start of what I did. But in general, it's something you actually have to kind of sit down and do for your own family. But I've given you step-by-step directions on that. So let's look at how do I use this. So what's a full match on the X chromosome? How many of you have uploaded to GEDMATCH some sort of autosomal results? Almost everybody. Well, good deal. I don't often get that. Most people say, what's GEDMATCH? So I'm glad that most of you are familiar with that. If you're not familiar with GEDMATCH, there are plenty of things online. Ask someone in the group maybe to help you. So it's not a difficult tool to use, but it is a lot like spreadsheets, and it can be kind of intimidating if you don't really know what you're looking at. I know in Columbus we do 2 GEDMATCH workshops a year, but we have one this Sunday, actually. This Sunday is our GEDMATCH workshop. So if you're interested in that, come up afterwards and we can talk about it. So the number of centimorgans per chromosome is determined by the Human Genome Project, some of the reference builds. None of that's really all that important. But the full genome in GEDMATCH is 3,783 centimorgans. That's your whole genome that's being tested. That's not your whole genome. That's the whole genome being tested at those 700,000 markers. A GEDMATCH full X match is 196. So why is it important to know that? Well, when you look at your results and you look in that X column on GEDMATCH, you're going to want to be able to decide if it's a close match or not. So what are the parameters? So it can be a 0, no match, and it can go up to 196, full match. And it doesn't matter which test you're using when you upload to GEDMATCH. GEDMATCH's mark is 196. I have included a chart here, and obviously we're not going to go through this with any great length, but at the very bottom, you can see FTDNA's match is 195.93, so it's basically 196 for a full X match. GEDMATCH is 196, 23andMe is 182. They have slightly different numbers involved there to consider it to be a match, but we're going to use 196 because we're using GEDMATCH for most of our results. These are approximations. I want to keep pointing out that this is population genetics. There are mutations, things happen. There's always some kind of funny end behavior on the chromosomes when they're duplicated. That can always happen. So I'll show you a case where my daughter and I actually don't match because of something weird that happens at the end of one of her chromosomes. I tell her that all the time. So you have this little out for being exactly like me. All right, so this is a GEDMATCH page, and I know this is kind of difficult to see. I've redacted like names and emails and stuff, but I want you to see from my kit, this is the one-to-one matching. I'm sorry, one-to-many matching. This is my kit, and what comes up first is my son. You see all the way on the other side in the red box, he's a 196 match to me. It's exactly what I would expect. I would expect that his one X chromosome that he has is a 100% match to me, or close. And anything in the 190s or, is considered close. My mom, the next person, April's my mom, she's a 196 match to me because I received one X chromosome from her, 100% intact. My dad, John, he's a 196 centimorgan match to me. So my dad is a 196 match to me as well, because I inherited one chromosome intact from my father. So that's as expected. It's just as important to look at the expected things as the unexpected things. So I have another kit. How many of you have more than one kit uploaded? So you might have Ancestry and Family Tree, or you might have 23andMe, and so you have two different kits. Some people actually upload the same kit over and over and over. Have you run into people like that? That you match them and it's 3 different A kits because they just forgot that they uploaded it, or they lost the number or something. But I actually have 2 kits up there. So good news is I match myself. I'm a 196 match to myself. And then my daughter is up here. Kylie is my daughter. She's a 194.7. Look at that, 194. Now I would expect her to be a 196. But like I was saying, with the end of each chromosome, sometimes they don't quite copy right. If you looked at a visual of it, what you would see is a break. It doesn't mean she has a piece missing. It just means there's a place where we're not exactly identical. And then it picks up again and we're identical again. So it's almost like having a 195 centimorgan match and then maybe a 2 centimorgan match. So it's kind of a combination thing. So all those are as expected, very normal. Now you can see there are other kits. There are people I don't know who they are. I don't know who Babetta is. I know who J.L. Dixon is. He's a cousin of my mom's. But there are some people on that list I don't know. But what I've done is I've sorted. If you see up at the top right corner, I clicked to show the X DNA matches from greatest to smallest. The default setting is the autosomal matches. So if you want to see your X matches from greatest to smallest, you need to click on that column. Every place that has an arrow there, or a little carrot-looking thing, those are all clickable things that will put things in order. And it'll go from alphabetical order, it'll go from centimorgan size. So each one of those, fiddle with that on yours. I used it this week because I had someone contact me and he gave me his email address. And I couldn't find him in the list. And I didn't want to search through, how many pages do we have of matches. And so what I did was I went to the email column and I clicked on it and did alphabetical email so that I could find him. Then I re-scrambled it so that I could see the results. But I at least knew where he was. So all of those fields are manipulated, can be manipulated. So eventually, if you go far enough down your list, if you've sorted on the X chromosome on the right over there, eventually you're going to see zeros. Those zeros are just as useful as the non-zeros. What that means, it's not exclusionary. It doesn't mean that you're not related to them on the X. Well, it means you're not related to them on the X, but you're still related to them. So it could be most likely that person is not related to you through your mom, but you never know. You can't rule it out. But the zeros can be really helpful when it comes to sorting with matches. And I show in that demonstration set that I sent how I use the zeros. Yeah, go ahead.
I have a question about uploading the GEDMATCH. The same person I tested my mother on FT and Ancestry. And I uploaded both the GEDMATCH, which seems kind of stupid now because it's the same thing. It's actually the same thing all the way down. So my 23andMe, if I upload that, is that going to be just wasting my time because it'll still be the same thing all the way down?
Probably, but it might be worth doing just because, remember we had back here, let me show you this, we had different kind of thresholds for different companies. Might still be worth doing. I think you're in general going to get the same result from having the duplicate kit. I haven't found yet where having mine duplicated gives me a different result. I have identical twins, and I've only tested, I've tested the second one now, but I only had one results, uploaded here, my son Casey. But he's an identical twin, so when I get Corey's test, you bet I'm going to upload that and see what happens. Because I'm sure, just with genetics being the way it is, with mutations and other things, he's not completely identical. There might be something that happens at the ends of the chromosomes or near the centromere or something else that makes me realize that they're not completely identical. And I tell them all the time, don't commit crimes and then think you're going to get away with it. You think I'm joking. Okay. They're 30 years old. You think that they kind of grow up a little. Okay. So let's look at the chromosome browser, and let's go to, oh no, wait, this is the chromosome browser, I'm sorry. This is my kit, and this is compared to visualization options for my son, my mom, my dad, my other kit, and my daughter. I want to show you this because the chromosome browser tool has 2D and 3D imaging. You've probably seen that, and it looks kind of confusing. So I just want to run through that. Well, and every time I think I know which tools are free and which ones are tier 1, they kind of switch them around. So, but this one's called the chromosome browser tool, and you can check different kits to compare against one another. And when I do that, I can get a 2D representation. So this is my son, my mom, my dad, me. You can see how they're almost all the same, but look at my daughters, how there's that weird piece there. Then you can do a 3D image of it as well. And you can see my daughters, my dad, my mom, my son, compared to mine. So kind of some weird tools in there. I'm not really as much a visual person as a chart person. So this, to me, seems a little bit cumbersome, but a lot of people just love the tools. So those are things that are available on GEDMATCH. And you can choose in the upper left corner the X chromosome, or you can choose chromosome number 5 or chromosome number 10. So if you're working on a project with a cousin who says, hey, we're related, we're on chromosome 15, we're from here to here, you can actually do a visual of that and see where the overlap might be. All right, so let's go back here to my dad's kit. So let's talk about who comes up on my dad's list. Now, thankfully, my mom doesn't come up on my dad's list. Okay, see, that took a minute, right? Okay, so my mom and my dad are not related, but remember, GEDMATCH has that tool, are my parents related? So you can actually check. Why would that be important? Does anybody know why it'd be important to know whether your parents are related? Yes. Yes, yes. If your parents are related, that's something called endogamy, or sometimes people call it a narrowing of the tree, or a compressed pedigree. A lot of different names for it, but you know, it could be cousins marrying cousins and that sort of thing. It doesn't mean that your mom and dad necessarily are cousins in the typical sense. It could have been pretty far back. But think about what happened with migration patterns, how many people were in the United States in maybe the 1600s. A lot of people married a lot of people they were probably related to. So it's a very common thing. But you want to run that test before you start making assumptions about mom's side versus dad's side of the family, because there could be some overlap. So this shows me my second kit, my daughter, and my son. So if you look at how the X match lines up, again, I'm a 196 match to my dad, which is what we would expect. That's the full centimorgan X that I got from my dad. My daughter is a 143 match to my dad. So remember, she has some weird end behavior, and she has a mixture of probably my 2 X chromosomes, a bigger portion from my dad than my mom. So she's got 143 or 4 that matches my dad. The balance came from my mom. And then she has another X that came from her own father. Okay, so she's got 1 X chromosome that's a mix. But you can see here, the vast majority of her X that she inherited was from my dad. If you look at my son a little bit further down the list, he has a 26 centimorgan match to my dad. So he inherited in his scramble, He didn't get an X from his dad, but from me, he got one that matches 26 centimorgans from my dad. The rest is from my mom. So he's got a much smaller piece that matches my dad. So does that make sense how you can use that information and you can say, well, what are the odds that my son and my daughter match on the same piece? They might, but they might not. Remember, every single time there's an egg produced, every single time there's a different mix that happens. So it doesn't mean that one got some of it, the other got the rest of it. It doesn't work like that with siblings. And I would assume that my son's twin would show the same exact match to my father, because they're identical twins. There is a visualization option that includes multiple kits. You can see at the top there the kits that I've included. I have 5 there. And I did what's called a matrix, an xDNA matrix comparison. I thought this was a really great visual for me. I'm not really the one that likes the picture. I like the chart better, so I'll show you that. But this is the matrix that we get. This would also show you if your parents are related. So this is like multiplication table or something where you're looking down and you're looking across. But if you notice, my dad and my mom are not a match to each other. Can you see that? Between my dad's kit, who's the first one, wait, not the first one, sorry, the 4th one, and my mom's kit, they're not a match to each other. So that's valuable information, whether your parents are related. Now, most of you probably do not have even one parent, let alone 2, in your database. But if you have children and you've uploaded your children, they'd be able to have a matrix that shows at least where they're related to you versus the other parent. My mom and dad have no centimorgans in common, so that's a big yay. That makes the math easier. My son Casey and I are a full match. He got 1 X from me and the other, 1 X from his, no, 1 X from me. The other X are a combination of my 2 X's. My son received no X from his dad, and he and I share 196 centimorgans, so that's as expected. My daughter and I are a full match, even though we're slightly off from that 196. She's at 194 or almost 195. She got 2 X's from me. She got an X from her dad. Sorry, she didn't get 2 X's from me. She got an X from her dad. And she got a combination of my 2 X's. We saw that already. We saw the piece that came from my dad, and then there's a small piece that came from my mom. So my daughter and I share 195 of the 196. That's considered a match. So you can view this information in a lot of different ways. You can view it as a visual 2D. You can view it as a 3D. You can view it as a matrix. So whatever it is that you need to use to view it and try to understand it, you can include however many kits you want in this matrix. So if you have cousins and second cousins and parents and children and grandparents, whatever you have in your database, you can choose as many kits. You can also choose from all of those people who match you and try to figure out how they're related. So it's not just people you know. I'm just using that because I think it's an easier example to kind of understand the science. This is an X, let's see. Oh, this is the same chart. My father and I are a full match. I received an X from my dad. My dad and I share 196. My mom and I are a full match. I received either one, the other, or a combination of her 2 X's. And my mom and I share 196. So all those things are as expected. What this chart tells us is not necessarily how I'm related to my parents, because those are expected results. It tells you kind of the split of what each child that I had received. So from his grandparents, my son shares 26 centimorgans, and my daughter with my dad share 144. With my mom, my son shares 171, and with my mom, my daughter shares 56. So you can see all those numbers on the chart. And I'm just using kind of rough numbers, not worrying about the decimals. You know, this is genetics, it's randomization, it's not precise, you know. So feel free to round. So let's talk for just a minute about the full and the half matches. Let's see how we're doing on time. It's almost 8. Okay. Because I do want to talk a little bit about the other case study that I sent you, just so that you can kind of get jump started on that. For full and half matches, this is something that comes into play with xDNA. When a man is comparing to a man, okay, so whether it's my father compared to my son or my son compared to some other man that he's matched to on xDNA. Remember, my dad has one X and my son has one X. So they're only comparing an X to an X. It's a little bit different case when you're talking about a man compared to a woman, because a man has one X, but he's comparing a GEDMATCH to both of her X's. So remember how my son is 196 matched to me? That's because GEDMATCH is taking the 196 and his X and comparing it to both of mine. Okay, so there is such a thing as a full match and a half match, depending on which kind of comparison you're doing. If you're comparing two women, if you're comparing a woman to a woman, then you're comparing one woman's 2 X's to the other woman's 2 X's. Again, you can sort using phasing. You can sort using some of the other tools in GEDMATCH, like the segment sorter. How many of you use segment matching? It's on the tier 1 side, I think. Okay, the segment matching tool is just amazing, isn't it? It's a fascinating thing. But that's what's going to help you differentiate which of those X's you're talking about. Or if you happen to have, like I do, my kid and my mom's kid, and then I have a phased kit with my mom as well, I can figure out exactly which points I match my mom, and which side of the family on the X chromosome comes from my mom, which side comes from my dad. So let me show you how to analyze. Now these are in your handouts, so I just kind of want to go through and show you a few things. But before we do that, let's see if anyone has any questions. Because we've kind of covered a lot of terminology, a lot of science words, and so far so good? Yes?
You did 2 kits. Are they different companies?
It doesn't matter whether you're comparing a GEDMATCH one company versus another. What I pointed out about the different companies and the charts of centimorgans in common has to do with the results that that company gives you. Once you move everything to GEDMATCH, regardless of your kit, 196 is going to be your X match on GEDMATCH. They should be almost identical because they're still testing the same roughly 700,000 markers.
Variation.
Well, that chart that I showed you, and it's in your handout, the chart that has GEDMATCH and it has family tree and it has those different comparisons will tell you how much plus or minus. Those last 2 columns, I believe it is, will tell you how much plus or minus they're off from one another. But if you look at your results in Ancestry and it says you have a 145 centimorgan match, and you want to know what does that mean, that's a different numbers system possibly than what GEDMATCH is telling you. But since most of us are uploading to GEDMATCH and using that, and the kids are all testing relatively the same number of centimorgans, then it can be standardized. Anybody have anything else? Okay. First thing I did with my X results is I did a little family tree. Now this is just kind of a rough family tree of just a couple of generations, but I think you'll get the idea here. I have a set of grandparents. William and Mary is one set, and Shields and Ada are the other set. And William and Mary had my dad. So his X is from Mary, most likely a mixture of her parents, and his Y is from his dad. Tree. Now this is just kind of a rough family tree of just a couple of generations, but I think you'll get the idea here. I have a set of grandparents. William and Mary is one set, and Shields and Ada are the other set. And William and Mary had my dad. So his X is from Mary, most likely a mixture of her parents, and his Y is from his dad. So dad's not involved. William is nowhere in this X saga, okay? If you look at me, if you go down the chart and look at me, I got an X from my dad, intact. And then when I had my children, they each got a mixture, probably, of me and what I inherited from my mom. So let's start at the top right. Shields and Ada are my mom's parents, so she got an X chromosome from her dad, intact. She got an X from her mom that's probably most likely a mixture of her parents. So now do you see how that fan chart is coming into play? How certain people are contributing and certain people are not. So if you can do your ancestry, even if you just do a rough write out or fill it in, I believe there's a PDF version online now where you can actually key in and then print. So you can do that with your family tree. That will give you an indicator of who the different possible contributors are. So from my mom, I get probably an X from my mom that's a mixture of her parents. It's probably not just her dad or just her mom. It's probably a mixture. And again, that's an assumption. And then my children, you can see that my son got a Y from his dad, and then my daughter got an X from her dad, intact. Now, their dad is deceased, so I can't test him. But if he were here, we'd be able to use that phasing and do a sorting, and I'd be able to tell from my daughter which piece came from dad and which piece came from me of her X's. But we don't have that. We can just phase my daughter with me. So what I call that is mother and other. So it gives us a mother tool, and then all the rest is other, so all the rest is dad by presumption, but we don't actually have dad's kit. All right, so I started with the tree. So you can do this at home. You can start with the tree. You can build out your fan chart, whether you do that online or you write it out, print it out. You can take it to like FedEx and get a big fat paper copy, where you can fill it in, or you can number it and list the names, however you want to do that. But it's important to combine this with your genealogy, with your family tree also. This isn't something that happens outside of the family tree. None of this DNA stuff happens outside the family tree. Okay, so what I did first, and I've written instructions so that you can repeat this at home, is I did a segment search, and this is again on the pay side, on the $10 a month side. And you can sign up on GEDMATCH for $10 a month, just for 1 month if you want. You don't have to have any sort of subscription. It doesn't automatically renew. It just tells you how long your month is, and then you can re-up it if you want. But this is on the pay side. So I did a segment search using the kit number. I set the centimorgan size larger than 7. I generally set it at 15 or 20. I just kind of go with the bigger numbers. The smaller the piece, the more difficult it's going to be to determine where it came from. So I just use that kind of as a rule of thumb. If the entire X is 196 long, a pretty significant 20 centimorgan match is a good place to start. I'm going to scan on just the X, but although this does work for all the other chromosomes. And then I always say no to the graphic, partly because it doesn't take as long to load. If you do graphics, it takes a long time, and also because I'm not particularly interested in the graphic. But I do get a nice table. So this is my X segments that are larger than 20 centimorgans. So there's only 20 of them. Or, I'm sorry, there's only 12? Wait, 12. Yeah, sorry, there's only 12. That's not bad, right? So all of a sudden, now you have 12 things to investigate, not 300, right? So that gave you a little heads up. And if you look at some of those kits, you'll see some common names there. My daughter, my mom, my dad, my son, okay, my other kid. And then you're going to start to see names that I don't know who they are. So those are the names that I'm really interested in. I already know how everybody in the top 5 seats there are related to me. I'm interested in those bottom 7. It's important to know whether they're male or female as well. And we'll talk about that. Some people do unidentified or unknown for their gender. I'm not sure why. Maybe they just skipped it when they were enrolling their kid. They don't know how to go back and fix it. But it is helpful to know if they're men or women. I'll show you that in a minute. So I inherited one from my mom, one from my dad. So what I did was I compared mine to my mom and dad, and it doesn't tell me anything. I know I'm a full match to my mom. I know I'm a full match to my dad. I know I'm a full match to my son and my daughter. So that doesn't tell me anything. But there are some matches that come up in that list, and I don't know which side of the family they are. And I've kind of color-coded them so you can see them as you go through. They kind of pop out a little bit, so maybe that'll help you identify when I've determined that I know which side of the family they're on. So I took my sons first. Now, why would I start with my son? Because he has one X. So we want to start with the simplest case, comparing the 1X and see what happens with his kids. So he has 11 kits that match, 11 segments that match. You notice again at the beginning are all the people we already know about. There are a couple other kits listed in there. Martha's listed twice, then my daughter, then CT somebody, then Donna, and there are a couple of Donnas, and then my daughter again. So you can see where he has segments that match. My son has segments that match my daughter in how many places? How many places do you see her name? You see Kylie there? 3 times. 3 different segments. From 2,300 to 12 million, they match. From 42 to 80, they match. And then at the very end, from 124 to 144 million. I think the total length is 156 million or something, so, I mean, close to the end. So there's 3 places where my son and daughter match. But that's what happens when you have recombination. They'll each have different places that match each other. They get different assortments, different random assortments from me. So Casey inherited an X from me and none from his dad. So either the X chromosome is exactly the same as my dad or exactly the same as my mom, or a mixture. So do you see how it helps to put people's names in there or their relationships in there to determine, okay, this person is a match, but it would have been the mother's father and the mother's mother, or one or the other, or both. So it's important to be able to kind of put your own names in there and your own family tree in there, and then you'll start to see that pattern. Remember, success is about organizing it and then analyzing it and looking for patterns. So really, it's not any more complicated than that. This whole 14-page handout thing took about, 20 minutes for me to do the screenshots and type it all out. The family tree took me a little bit longer because I wanted it to look a little pretty. But everything else really, it didn't take long at all for me to do this analysis. So if you look at my son's X chromosome, from the beginning to 12 million, there's a break, and that piece comes from my dad. And then from 12 million to the end is from my mom. So we can actually tell which pieces come from my mom and which pieces come from my dad. And then we have these other people that match one or the other. And then we can determine that Martha and CTC and Donna S, are all related on my mom's side because their match is in that longer piece that was from my mom. So we just systematically, we're not going to go through every screen here, but we systematically analyze each person on the chart. We analyze starting with the men because they only have 1X, it's easier. And then we start determining which piece came from which person. You may not know. If you don't know it came from mom or came from dad, you at least know it came from 2 places. So you don't know necessarily which is which yet, but you know that it eventually comes from 2 places. So this is what I mean by just kind of being organized, writing down some numbers, looking at it, analyzing it. And eventually I got to the point, we'll go down to the end, where I had a list here. Let's see, here's the list that I got. the summary of all the people who matched, I was able to determine that some people matched my mom and me, but I'm not sure if it's my mom's mom or my mom's dad, because I don't have their DNA. Martha definitely matches myself, my mom, and my son, but I'm not sure again if it's that mixture, if it's just my mom's mom or just my mom's dad or a mixture of the two. I know that Babetta matches my mom, but that didn't get passed down to me. So she matches my mom. Again, I don't know where she matches my mom, but it didn't get passed to me. And then, of course, if I don't have it to pass on to my children, they don't have it either. So I went through the list, and I made a list of all the people who matched all of us and just started sorting who matches who matches mom, who matches dad, who matches another cousin. So that's how you analyze it a little bit at a time. Once you have something like this, then you start emailing people. And you say, look, here are 3 people, CTC, Donna, and Donna S. We also have my mom, me, and my son. So there's 5 of us in a group. We all share the same segment. So let's email about all 5 of those kids. So what do you have in that spot? What do you have in that spot? And we can do segment analysis just with that one segment and figure out who matches the 5 of us. So it's just a process of going through and analyzing step by step and then determining what piece do you have in common and trying to get to the point where maybe you're comparing family trees. So it's not complicated, but it is cumbersome. Does that make sense? It's kind of over and over. The reason why I do the charts like this and kind of the running dialogue with myself is so that I can come back to it. Because if you do this enough times with enough kits, you're going to forget where you were. You're going to forget whose kit you looked at. You're going to forget the kit number. You're going to forget the segment. And then you're thinking, where did I see that? So I do that sort of capturing all along the way as I'm investigating. And then I have something to come back to. But then if someone like Babetta or someone like James contacts me and says, how are we related? All of a sudden for James, I know that he matches my mom. He's got a longer piece than my mom. He's got a match to me, and then he matches a bit smaller piece of my daughter. But I know automatically that James is a match on my mom's side. So it gives me something to go on with how am I related to James. So can you see how maybe there are 2 things involved here? Getting organized and analyzing and looking for patterns is one of them, but also kind of keeping your paper trail and having some way that you do it. This may not work for you. Maybe you have another way that works for you. But find a way that works for you so that you're not reinventing this over and over or rediscovering or reconfiguring or doing it again and that sort of thing. Now, you know if you have new matches, they could fit into this scheme somewhere. So that's another thing that's a little bit difficult with GEDMATCH because you have to kind of manually look at those new matches every time. But this will give you a good start. Plenty of work to do before you even investigate the new matches. So let me see if you have any questions since we're going to wrap up here. Yes?
So